Okay. I think we might. How many people do we have here? Oh no, we're still missing a couple. All right, we'll just wait maybe 1 or 2 more minutes. I think there should be a total of 11 here now. So cool. Do 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 do. All right. Yeah, hello again. I think there's a couple of new people, right? I think Ram, you're joining. Am I saying it? Is that correct, Ram?
Yeah.
Okay, great. And then Alan Wong?
Yeah, that's me.
Okay. Were you here yesterday, or am I just
Yeah,
totally...
I joined late. Sorry about that. I didn't know it
Oh
started.
no, not a problem at all. I just want to make sure that I'm not insane and imagining. So I remember Samuel, I remember Ryan, I remember Richard, I remember Alice, Ethan. Ethan, were you here yesterday?
Yeah.
You were. Oh my goodness, I'm so sorry. Okay, I remember Peter doing this now. All right, cool. Yeah, well, I guess we'll go ahead and get started then because it's 10:03. So let me go ahead and share my screen. All right. Can you guys all see a screen with a PowerPoint on it? Yeah. Cool. All right. Yeah, and same thing as yesterday. If you guys wouldn't mind, and if you have a camera and you wouldn't mind showing yourself, again, please do. It just makes it easier when I'm talking to people as opposed to just black boxes with names. Plus, it also helps me because if I know that I'm explaining something correctly, usually I'll see like subtle nods or like eyes open. But if people are confused, I'll notice people are like maybe less engaged. So it actually does. Someone else is in the waiting room. Oh, Andrew. Okay. All right. Okay. Andrew, hello, welcome back.
Hello.
All right, cool. So yeah, let's go ahead and get started. Let's see. So yeah, so day 2. Yeah, so here is today's plan, I suppose. This is what I have for us today. I figured we'd go through some of the frequently missed questions on the last problem set. Again, I didn't put a due date for that. I don't think I didn't think it was necessary to put a due date because I think you can go back and do the problems whenever you want. But generally, what I think we'll do over the next couple of weeks when I see you is we'll have the problem set, right? We'll go through it the next morning. The previous day's problem set, we'll do it the next day. Just go through the ones that were missed. So, maybe it's a little bit of incentive to get it done before the next class because we'll go through the answers to some of the more difficult ones during the next class. So yeah, so we'll do that today also. So yesterday's key concepts, if you remember, we did Newton's laws yesterday. Right, we did Newton's laws and a little bit of dynamics yesterday. Today we're going to do kinematics and some 2D motion. And by 2D motion, I mean mostly projectile motion and also some uniform circular motion. Those are both examples of 2-dimensional motion. We'll go ahead and do the quiz again, right? The diagnostic quiz on these topics, the kinematics and 2D motion questions. We'll go over the quiz for about 10 minutes. Any of the questions that were frequently missed, we'll go ahead and go through those questions. Then we'll just go over some guided F equals MA questions again. I tried to find some difficult questions from past exams, and we'll go through them, and I will give you what my solution to those questions were. And then we'll just end with some general questions, or if we have time, we can maybe address other problem set questions. I don't know. I don't know if Eric is joining us again today, because I do know that he put something in. I think he put something in Google Classroom of like some other questions, but I don't know if he's gonna talk about those or not. But I don't see him here yet, so that's fine. Anyway, cool. So you guys can see two questions on the screen, right? These questions may look familiar. These were two questions on the problem set yesterday. These were the two most frequently missed questions. So actually, I will, just let you know, no one actually got this first question right. And that's not a problem. I'm not saying that in any, bad sense. It's actually it's a tricky question. So everyone is in good company. So let me, so I think it might be worth going through this one. Can we draw? Oh yeah, we can draw. And then the second one is also one that might be worth going over. Where can I put this? I'll put it down here. All right. Cool. So everyone remembers these questions from yesterday. Why? Oh, there we go. Yeah, this is what I want right here. Hold on, let me get rid of this. I don't need this here. All right. So let me move this. Can't move it with the pen. All right. So yeah. So the first question that we had yesterday was, if a planet of radius r spins with an angular velocity omega about an axis through the North Pole, what is the ratio of the normal force experienced by a person at the equator to that experienced by a person at the North Pole? So assume a constant gravitational field and that both people are stationary relative to the planet and are at sea level. So I think everyone understands that if we have a planet, that's not a bad circle, right? That's a pretty good circle, if I do say so myself. So yeah, so here is the North Pole, and we're saying that this planet is rotating about this North Pole with some angular frequency or angular velocity omega. And if we have a person standing on top of this planet, oh, my North Pole is a little bit in the way, but let's imagine that if we zoomed in here, we had a person standing on top of the planet. They're not really rotating about, they're not rotating in the same way that a person is rotating out here, right, on the equator. Like a person rotating on the equator here has some, like an orbital angular velocity around this rotation axis here. But in the case of a person standing at the North Pole, through the North Pole, the rotation axis is now through them. So they're not going to have a centripetal force in the same way that the person at the equator will have a centripetal force. And that's going to become relevant when we try and write the equations of motions of these two people and then take the ratio of their normal forces. So, so the person at the top, right, North Pole, his equation of motion is just going to be N equals mg. There's only two forces acting on this person, right? You have a normal force from the Earth pushing upward on the person, and then there's a gravitational force on the person exerted by the Earth, right? So these two forces here, remember, this is what we discussed yesterday. Whenever you write the equation of motion for an object, in this case the person, you're only considering the forces on that person, and there's only two forces on this person: a normal force exerted by the planet on the person, and a gravitational force exerted by the planet on the person also. Now just keep in mind, like we said yesterday, these are not the third law pairs of each other, right? These happen to be equal and opposite, right? These happen to be equal magnitude and oppositely directed, but they are not the Newton's third law force pairs. And if you have any questions on that, please let me know. We got Eric Kwan. So yeah, so just keep that in mind when you have examples like this. So this is the equation of motion of the person at the equator. Now let's draw the equation of motion for this, or write the equation of motion for this person who's going to be at the equator. I'm sorry, this person at the pole, this person will be at the equator. Right, the equator is the imaginary line right about there. So, well, let me ask you guys. So what are the two forces on the person at the equator? What forces are on this person?
Centripetal weight and normal force.
Yeah, but okay, so be very careful though. The centripetal force is not a new kind of force though, remember. So there's only two forces acting on this person. There's the normal force, and you were right about these other two. Then there's the normal force, and there's the gravitational force, right? The person's weight. Those are the only two forces on this person. Centripetal force means that the net force of those two forces, the vector sum of those two forces, is what's keeping them in a circle. So just keep that in mind. Centripetal force is not a new kind of force. It's not a force that acts on someone. It's the name that you give to the net force maintaining circular motion. Right? That's an important conceptual note. Centripetal force is not a new force. It's not its own kind of force. It's the name given to the net force that maintains a circular orbit of an object. So with that said, let's go ahead and do it like this. Oh, so one actually useful thing is that when you know something's moving in a circle, right, it's usually most useful to define radially inward as positive and radially outward as negative. Which is why what I think we're going to do here is we're going to say that if we call radially inward positive, what would be the positive force in this case?
mg, or gravity.
Yeah, so mg, m minus mg, yeah, so mg would be the positive force in this case because that's the one radially inward towards the rotation axis. And then that would leave you with the negative force kind of in this case, which we would be left with the normal force, right? So it's the sum of these two forces, F equals mg minus n. This sum is what's going to equal the centripetal force. And you can write centripetal force as mv squared over r, but in this case, they don't give us v and r. They instead express things in terms of the angular variable omega, which is just going to then be m omega squared r. Are there any questions about how I got to that? No, okay. Excellent. So then, cool. So we now have our two equations of motion for these two people at different points on the planet. We have n equals mg, and we have mg minus n equals mv squared over r. And again, we chose this strategically, right? We chose mg minus n strategically because we want positive to be inward. And one of the common mistakes, I suspect, I didn't look at the distribution of answers for everyone, but I think one of the common mistakes might have been writing n minus mg, which you can do it that way. That'd be fine to do it that way, but if you did it that way, you would have to then include a minus sign on your centripetal force. But if we invert the coordinate system and make radially inward positive, then you don't need that minus sign. So anyway, so if n equals mg here, then that means n for the person at the equator is going to be m omega squared r. Oh, hold on. It's going to be mg minus that. Mg minus m omega squared r. They're calling it a capital R. So, are we in agreement on this? Okay, great. And now if we take the ratio of these two, of this equation here, this is the normal force at the pole, and then this is the normal force, oh my gosh, this is the normal force at the equator. This ratio, and what do they want the ratio of? They want it at the equator. Okay, so they want equator on top. So it's going to be mg minus m omega squared r over mg. Does that make sense? So we have a yeah. So is this everyone comfortable with what we have here? This is the ratio here. So if I rewrote this just a little, let me erase this just so we have a little bit more room. So if I wrote this ratio, so here is normal force at pole over normal force at equator. Oh shoot, it's the other way around. Normal force at equator over normal force at pole. And anyway, this becomes 1 minus omega squared r over g. Cool. Everyone happy with that? I think it was common that people put a plus sign here. I think that was a common mistake, and I think that stems from possibly writing n minus mg, right? So you have the normal force being positive, but then you didn't make the sign accommodation on the centripetal force, which is that's a subtlety, so don't worry. Anyway, so that's how you would approach that one. The key takeaway here is if you have motion that's inward, it's usually most convenient to define the inward acting forces as the positive direction, if you're going to keep this as a positive value here. Cool. Any questions on that? No. Okay. All right, let's go ahead into the next one that was most commonly missed. So two springs both have spring constant K and a relaxed length 0. So these springs don't exist, I guess, at 0 length anyway, but they are each stretched to length L and then attached to two masses and a wall as shown in the figure. The masses are simultaneously released. Immediately afterwards, the magnitudes of the accelerations of the left and right masses are, respectively. I didn't include the answer choices here, but we don't need them. That's okay. So let's go ahead and write out the equations of motion for both of these masses. So let's go ahead and start with this one. What's going to be the equation of motion for that mass, the one that I just circled? Let's go ahead and also call this direction to be positive x. Let's start with this. What are the forces acting on this circled mass?
The spring force from both directions.
Right, yeah. So there's two spring forces, and so if we go ahead and I don't like that sigma. Let's try that again. That's a little better. All right, so the sum of all the forces then in this case are going to be, yeah, you're going to have, also it might be useful to write out Hooke's law here, right? So everyone remembers Hooke's law, right? F equals kx, the magnitude, right? Remember, this is magnitude. If you did this with a vector, there'd be a minus sign there, but the magnitude of F is k times x. Right. So, yeah, well, this is going to be k times x from this spring minus k times x from this spring, right? Because now it's the same magnitude force, k times x, but acting in the actually we should probably say L. I'm sorry, yeah, because they gave us the lengths here. So this would be k times L. K times L minus k times L equals ma. Right? So you have a k times L force this way, and then a k times L force this way. Right? And look at that, that turns out to be 0. And you know that m is non-zero, so that leaves us with the only other possibility that a is 0. So the acceleration of this mass initially, right at the start, we're only talking about the instant that this system is released. The acceleration of this mass will initially be 0 because of the competing forces of these two springs. This would not hold true for all time t, right? I mean, after a long time, you know, some stuff would happen because of the fact that there's a solid wall here, but this is not F equals MA stuff. So anyways, let's go ahead and draw the mass then for, or write the equation of motion then for this mass. Well, this time it's going to be KL. I mean, if we want to be technical, it'll be really negative KL, but they're only asking for magnitudes here, but we'll take care of that later. And this is going to be MA. So if you solve for the acceleration of this one, you get KL over M. And I'm taking the magnitude, so the minus sign can go away. So there was your answer. There should have been an answer choice that was 0 and KL over M. I don't remember which one it was, but that should have been an answer choice, and that would have been the answer. Cool. All right. Any questions on that? No. All right. Then let's proceed. Oh, I gotta stop annotating. Yeah, it's a little annoying. All right. So okay. So today's focus, like I said, we're going to do kinematics and two-dimensional motion. I think all these should be familiar to you. If you don't have these already memorized just through using them so frequently, it might be worth keeping these in the back of your head, especially during, you know, like an exam like F equals MA, because of all the questions, there's 25 questions, at least 5 of them are going to make use of one of these equations. You know, so yeah, your kinematic quantities are V, well, final velocity, initial velocity, A, T, and delta X, which is displacement. If you know any 4 of those quantities, you can usually find the 5th one. Well, you'll always be able to find the 5th one using one of these equations. You just need to choose the equation that fits the variables that you have. And then so really quickly, I just want to do an average velocity question just in case we were missing those. Also, where is my, why doesn't my thing pop? Oh, there it is. Okay, cool. So just really quickly, let's just run through this one really fast. So the coordinate of objects is given as a function of time, right? You have 8t minus 3x squared, or yeah, 3t squared, where x is in where x is meters and t is in seconds. It's average velocity over the interval from t equals 1 to t equals 2. Now, I actually want to do this both ways with you guys just to verify the correctness of that equation, right? So the average velocity equation, we said this. We said that the bar just means average, right? This right here, this is the definition of average velocity. This will always give you, if they ever ask for average velocity, this will always give you the correct answer. This 1/2 V plus V naught, V final plus V naught, I should be more specific. This is only true in constant acceleration. This is always true. This is only true in constant acceleration. But it happens to be the case here that we have constant acceleration, right? I don't want to take, you know, but for those who've taken calculus, right, if you take two derivatives of this, you get a constant. So there's constant acceleration here. So both of these, so either of these methods would work, right? So let's just go ahead and quickly do this. So we have x equals 8t minus 3t squared. So the final x value, x of 2, what's this going to give us? This is going to give us 16. Let me draw a better 6 there. 16 minus 3 times 4, right? And this is going to be 16 minus 12, which is 4. And then x minus 1, or x of 1, is just going to be 8 minus 3, which is going to be 5. Does this make sense? Yeah, so x of 2 is at 4. Yeah, so you plug in 2, you get 16. Yeah, okay. Yeah, and then so if you do delta x, you do final minus initial, you're going to end up with 5 minus 4 over 2 minus 1, and you end up with negative 1. Does everyone follow? Okay, and then if you do the exact same thing, right, if we take a derivative of this, you're going to end up with 8 minus 6t, right? And so if you haven't taken calculus, don't worry too much. Like this way would have been perfectly fine. This is just a way that I want to show you, just to show you that this also works. So the velocities have to be at t equals 1. So v of 1 at the start of the interval is 2, right? It's going to be 8 minus 6. But then at the last part of the interval at t equals 2, you get 8 minus 12, which is going to be -4. And if you take the sum of these two, right now, if we use this equation, 1/2 v final plus v initial, you get 2 minus 4, which is -2, over 2. So you get -1 anyway also. Cool. Any questions? I don't want to spend too much time on that because I think these are some of the ones that you guys already will know. Cool. Make sense? All right. Yeah, and then these are some of the other 2D equations, 2D motion equations that I suggest you keep handy, right? Especially in some of the problems that we're going to do later in probably a few minutes, the projectile motion problems. Having these equations handy is generally advised because you can definitely rederive these, right? You can rederive these whenever you want. Like whenever I do a projectile motion problem, I generally just rederive these, but if you have these handy, that'll help. And then a circular motion question, or circular motion equations, these are just the kinematic equations again, but in terms of your angular variables, right? So all of these are the same equations that we just saw 2 slides ago, but now with your angular equations. Does that make sense? Are we all on the same page? Give me a thumbs up if you're good. Good, 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 good. Okay. All right. I will assume that we are good. And then, yeah, of course, you have your uniform circular motion. This is the same equation that we just used on that one question with the rotating planet, except we used mv squared, or this is mv squared over r. You could also use, like I said, the other version of this equation, which is m omega squared r. Right? That's an omega there. And does it make sense how you go back and forth between these two? Right? You would just substitute v equals r omega. V equals r omega into this first equation, and then you would get back m omega squared r. Okay, great. So here's a quick conceptual uniform circular motion question. So take a quick look at that. Here all drawings. So, which one of the following statements is not true for uniform circular motion, for constant speed circular motion? So I'll let you guys read through these answer choices actually, and then I will be eager to hear from one of you on which one is not the correct statement for uniform circular motion. Yeah, so what are we thinking? V is perpendicular to R.
C.
C. Yes, okay, that is correct. And so what's our reasoning for that one?
Well, A is right, and so is B. C is wrong because it's tangential.
Right, yeah. Yeah, that's exactly right. So if you have a circle, if you have a particle or something, an object moving in a circle, right, you'll always have your velocity vector is tangent to the motion, tangent to the path. Your position vector is drawn from the center to the perimeter where it's located, right, where the particle is located. And then your acceleration is anti-parallel to the radial vector. Cool. That's right. And Yeah, and so R, so that is the right magnitude for V. It is R times omega, but it's not directed in the same direction as R. So, but actually, I'm curious. I have a follow-up question for this one. We're not done with circles just yet. So, which of these statements is actually always true? So, all these except one were true for uniform circular motion, but what about non-uniform circular motion, right? Because what if I'm rotating something in a circle, but I'm imparting on it some, angular acceleration so that it's not moving in a uniform. It's not moving at constant speed. It's not uniform circular motion because there's an increasing speed. Which one of these then is always true?
Is it A?
Yeah. So why do you think A?
Because for B, like when there's angular acceleration, then it changes up like the net acceleration, and then for basically D, it obviously is uniform. So if it's non-uniform, you can't use that equation. And then E is it's using like the rolling without slipping formula, which is V equals R omega, but that can't be applied.
Right. Yeah, no, so that's exactly right. When you have an angular acceleration, right, there's going to be other components to your acceleration now. In uniform circular motion, you just have a centripetal acceleration, right, radially inward. But if you have some angular acceleration, there's now an additional component to your acceleration, and then that's going to interfere with the magnitude. The total magnitude now will no longer just be v squared over r. So that's exactly right, Alan. All right, good. So I feel like we have a decent grasp of this. Let's go ahead. Oh, clear all drawings. Why is this not clearing? Oh my goodness. All right. Anyway, let's go ahead and let's do that. Let's do the quiz. So everyone should be in Google Classroom, and there should be a quiz, I think, visible to you. I assigned it before the class, so it should be visible to you under the next topic, right? Kinematics and 2D motion. Does everyone see it? Yeah? No? Everyone see it? Yeah? Okay. Great. Let's go ahead and spend a few minutes on that. I said 15 minutes. I'll cut us off if we're done before 15 minutes. That'd be great. That'd be fine. But if we happen to go the full 15 minutes, that's also fine. So cool. At 10:50, we'll go ahead and go over these. So. Okay, we'll give it about 5 more minutes or so. So if you're not almost done, consider wrapping it up. You still have a few minutes though. No need to rush. No need to rush. Cool. Okay, let's go ahead and give it maybe 1 more minute. And again, I just want to emphasize, if you don't get all of them right, that's totally fine. But I also want to make sure that we go through the ones that were difficult, if there were any that were difficult. And also, I want to go through the actual difficult questions that we have today, because there's actually some cool questions today that I have selected. So I want to go through all of them. So, all right, cool. Everyone's in. Awesome. All right, pretty good. Looks like everyone. Yeah, so it looks like everyone did really well. But it looks like okay, so oh darn, okay, so one of these looks like it was causing consistent difficulty. So let's go over this one really quickly. The first figure below shows the A versus T. Yeah, let me go and share my screen and let's go ahead and go over that one really quickly. Okay, can we see my screen? Yes, yes, no, yes. You guys are a silent group, aren't you? Yeah, okay, we're give the thumbs up. Hit him with thumbs up. Also, just give me 1 second here. I need to find the question now because I have to draw the graphs. Well, see, this is because there were more graphing questions that I was going to put on the problem set that you guys have later, and there were some graphing questions that I was going to do here in class. I didn't know how well equipped we would be with graphs and whatnot, but I do think there's actually one graphing question on your problem set, so we can take a look at that one. Also, where is the question at? Oh, found it. Okay, cool. Let me draw this out really quickly. All right, yeah, let me try drawing this out. Annotate. All right. So we have some graphs, right? And that's not a good set of axes. So we have A versus T. We have V versus T, right? And we have X versus T. And I want to know, Alicia Lynn is joining the room. Do you guys hear a loud bing bing when someone enters the Zoom meeting, or is it just me who hears that? No, because when I hear that noise, that was that surprised me. I didn't know if anyone else heard that or not. But anyway, so let's go ahead and finish drawing these graphs. So they look like, so it looks like this and this, right? Looks roughly like that. And I should probably make it clear that there's a maximum here. Maximum. And I should probably make it clear that there's a minimum there. All right. And then here. Cool. All right. Does everyone understand what I'm drawing here with the graphs? Okay. Great. Well, I will say that this is, I mean, fundamentally speaking, these are actually calculus questions. I mean, this right here is technically a calculus question. Now you can gain an intuition for these sorts of things not knowing calculus, which is what I'll try and do here. I'll try and give you an intuition not using calculus. But if you know calculus, this is definitely made a little bit easier. So the question is, I want to know where all points on these curves necessitate zero acceleration. By the way, who has taken calculus? Who has taken like a introductory? Yeah, I'm just curious how much calculus exposure we have in this group. Yeah, okay. So it actually looks at the, so either either we don't have a lot of calculus exposure, or people don't want to disclose whether or not they have calculus exposure, which you know, totally fine. So anyway, well, we know here this is for sure going to be a point where there's no acceleration. I don't think anyone disputes this, right? We have the acceleration versus time graph. The equation of the t-axis here is a equals 0, right? So it's very easy to tell where there's zero acceleration on an acceleration versus time graph. And I believe this was what, point B? So point B should have been one of your selected answers. Oh, no, I don't want that. Yeah, so, all right. Yeah, point B should have been one of your selected answers. Okay, now, can someone tell me, if you were given a velocity versus time graph, if I gave you a velocity versus time graph, how would you identify the points where there's no acceleration on that graph? If I gave you a v versus t curve, how do you identify the points of no acceleration?
The derivative of the graph is 0.
Okay, right, that's true. And so when the derivative is 0, what does that mean on the graph though, right? So assume I don't, you know, I don't know calculus. What's a derivative?
It's where the slope of the graph is 0.
Right, right. So what Ryan, wait, was that Ryan who said that, or?
Yes.
So yeah, so that's exactly right. It's where the slope of this graph is 0. And, you know, so let's do this without calculus, right? We know that the definition, right, of velocity, or I'm sorry, the definition of acceleration is roughly delta v over delta t. Right now, this is actually the definition of average acceleration. But you know, when you get a small delta v and a small delta t, it becomes the definition of acceleration. So we want to find points where the change in velocity over a time interval is very nearly 0, right? And that happens to be the case where you have what's called local extrema on your v versus t graph, right? And that is exactly as Ryan said, that's where the derivative is 0. So there's 2 points where that's the case, right? If I drew a tangent line right here, the slope of this tangent line is 0. There's also another point where the tangent line has a slope of 0, and it's right there, but I also drew it a little lower than I wanted to. It's roughly right there, right? So I drew 2 tangent lines, and at these 2 points, you have a slope of 0. These are the 2 points where v over t, or delta v over t, delta t would be 0, right? Because if I took a small little step along the t direction here, I would get a delta v of almost 0. So there's no acceleration here. Same thing here. If I took a small step, an infinitesimal step along the t direction, a small step in delta t, there's almost no change in v. Now that's very different over here, right? If I took a small step in t over here, there's a very noticeable change in v, right? So there's clearly a non-zero acceleration here, given by the slope of this tangent line. But where you have local minima, such as you do here, or local maxima, such as you do here, also called critical points, you'll have a derivative of 0, which means that the acceleration will be 0. And I believe what points did these correspond to? What letters? These were letters E and H, right? So E and H should have been 2 other ones that you included in your answer. Are we all on the same page? Okay, great. Now I definitely, the most difficult one, I would say, is this next graph, right? Position versus time. And so again, I hate to use the calculus terminology if we don't all know calculus, but the second derivative of position, right, is going to be acceleration. Now, just the unfortunate part about this whole thing is that humans in general don't have a very good intuition for second derivatives. We understand rates of change. We don't really understand rates of change very intuitively, right? So when I talk about the second derivative here, and I ask about, or when I give you the position versus time graph, and I ask about properties of acceleration, which is 2 derivatives away from position, it's not exactly an easy question. But nonetheless, there's a point here, right, where it appears that the position is increasing more rapidly before this point, and then it's increasing less rapidly after this point, right? And there's a special name given to this kind of point. And does anyone know what the name of this point is?
Inflection point.
Right, yes, it's an inflection point. That's exactly right. And who's heard of that term before? I mean, am I using foreign languages here, or is everyone understanding? Okay, all right, so some people have heard of it. Okay, great. So inflection point, the definition of an inflection point is where the concavity changes. And the concavity means that, well, here you have a concave up function because it looks like it can hold water, right? This is how I learned calculus. If it looks like it can hold water, it's concave up. If it would drop water, as it would do here, it's concave down. And so the point where that concavity changes is where the second derivative would be 0. And that is how you know where the acceleration is 0. Yeah. Intuitively, it's not so easy to see, but let's go ahead and draw the velocity versus time graph here, and hopefully try and figure out what the position versus time graph, or the acceleration versus time graph would look like after that. And let's hopefully find that this will line up with a equals 0. So if we're going to draw the velocity versus time graph here, we're really just going to be graphing the slopes, right? We're going to be graphing the slopes of this function. So we know that there should be a 0 here. There's going to be a 0 here. There's going to be a relatively high slope at this inflection point. There's actually going to be a local maxima here, right? Whenever there's an inflection point on your function, that means that there's a local extrema on your derivative. And it's the fact that there's a local extrema here that gives you a 0 on your derivative of this first derivative, which is the second derivative. But anyway, so there's a negative slope here. So we're going to want some negative values here. 0 here. Then we get some positive values here. yeah, so there's still positive slopes here, but they're less positive, and then here we get back to negative values. So look at that. So I drew this really quickly, but this is roughly what your first derivative would look like. Do we all agree with that? In other words, if I gave you a position versus time graph, which I did here, and asked you to find me the velocity versus time graph, you would essentially be graphing the slopes of this first function, which is what we did here, right? Negative slope, negative value. Negative slope, negative value. Zero slope, zero. Positive slope, positive value. Very positive slope, right? The most positive slope of this whole thing. Inflection points indicate the maximum rates of change on your function. Inflection points are where the slope is greatest or least, right? The magnitude of the slope is greatest at inflection points. So then you have, greatest slope here, slightly smaller but still positive, slightly smaller but still positive. Those are these 2 points here. Zero slope yet again here, and then negative again. Great. Okay. Now let's draw the first derivative of v of t, which is the second derivative of a of t. What brave soul wants to do this? What brave soul wants to describe to me what the graph of this acceleration plot will be?
Straight line from some value in A, and then it suddenly drops down to a value below 0.
Right, yeah. So so you have a slope here. Technically I drew this kind of poorly. This really should, I should have made this look more parabolic like, I guess. I would say that the first derivative would look something like this. You're right that it's going to be a straight line, Ryan. And there's going to be a 0 corresponding, let me try and draw this a little better. There's going to be a 0 corresponding to the maximum, which is going to correspond to the inflection point, which I had to shift it just a little bit to make that happen. But yeah, so here we have a very positive slope. Here, technically have a slightly less positive slope, right? If you have an upside down parabola, which is what I was going for here, more positive slope here, slightly less positive slope. So, you're going to have a graph that looks something like this. I'm not saying that this is necessarily a cubic function, or yeah, because this would have been cubic if this was going to be linear here, but maybe it was. But yeah, so the first derivative looks something like this. Anyway, the point of this whole exercise was for the non-calculus students, how you would get acceleration from a position graph. I think the best thing you can do is first try drawing velocity, right, which is graphing the slopes here, graphing the rates of change, and then from your velocity graph, trying to graph acceleration. And I hope that makes sense, because that is a question that you may encounter. Is everyone comfortable with that? So, I guess I should say what the final answer is then. What was this? This was point K. So your 4 points then were B, E, H, and K. So some of you, it looks like you selected B, E, and H. So you got this, and you got this, but the tricky one was the inflection point here. And I just want to make it clear, going from position to acceleration directly, I don't have the mind for that. Maybe Isaac Newton would have been able to do that. Maybe Euler could do that. Some of you could certainly possibly do that. Not me. I have to draw the velocity graph, and then the velocity graph go to acceleration. And from that, you can see that you get BEHK as your 4 points for which there's no acceleration. So, good. I hope that makes sense. I will clear all the drawings. I think that was the only one that was consistently missed. So other than that, great job with the quiz. Looks like you guys have a grasp of it. So let's go ahead. So we have about an hour left. Let's go ahead and jump into the questions that we have planned for today. So these are some of the more, I guess, difficult questions or interesting questions from past F equals MA exams that I found, or from, just other sources in general. But I think that these ones might be useful to go over. So let's go ahead and take a look at this one. Let me get a drink of water first. Stay hydrated. My mouth's very dry. It's actually lemonade. And it's that powdered stuff, right? You put in the powder and you get lemonade out of, or yeah, pink lemonade out of it, which I've heard is actually a little worse for you, right? Because of that, heard that actually like might dehydrate you more. I don't know. That's what someone told me. Maybe they're just trying to scare me. Anyway, so a ball of mass m is launched into the air, and we're going to ignore air resistance, but assume that there is a wind that exerts a constant force F0 in the negative x direction. So let's go ahead and first address our coordinate system. I'm going to assume our coordinate system is like this. I'm going to make this the positive x direction, and I'm going to make this the positive y direction. I'm also going to make our origin the point where the ball starts. I think that's the most convenient choice of coordinate system here. In terms of F0 and the acceleration due to gravity, at what angle above the positive x-axis must the ball be launched in order to come back to the point from which it was launched? So essentially they're asking, we're going to launch the ball here, but we have a force vector this way, right? Negative F0 x hat. What angle must theta be so that this restorative force, negative F0 x hat, brings me back exactly to the origin? Cool. So I think what we will do in approaching this problem is I'm going to do it with calculus really quickly, but we'll stop using calculus at about the 5th way mark, and then we'll just use kinematic equations from there. Actually, you know what? No, we'll just use kinematic equations. There's no need to complicate this. So let's go ahead and write out our kinematic equations for x and y. So I'm going to write out the position functions for x and y. And the equation that we're going to want to use is x0 plus v0 cosine of theta. Oh, hold on. Actually, I don't want to do that. v0 t plus 1/2 at squared. This is the equation that I'm alluding to here. This is the one that you're going to want to use. So we're going to write this equation for both the x direction and the y direction, right? We're going to essentially break this into components, right? In two-dimensional motion, you want to break your motion into two components, right? An x component and a y component. And you want to have separate equations for each one. So if we're going to address the x direction first, what is x0, our starting value of x?
Zero.
Right, 0, right? We said we're going to start at the origin, right? So it's going to be 0. We didn't have to do that, but we'll go ahead and do it that way. So that's right. What about v0? Whenever you have, this is essentially projectile motion. Whenever you have projectile motion, what is the x component of the initial velocity? Or the x component, yeah.
V0 sine or cosine theta.
Right, v0 cosine theta, that's exactly right. v0 cosine theta. And then in normal projectile motion, this is all, there should be a t here. In normal projectile motion, this is where we stop as far as x is concerned. But we don't stop here this time, and the reason why is we have a force now in the x direction. So what is our last term going to be on this x equation? And Ryan, I'm going to ask you to not answer, if you wouldn't mind. Someone else, what brave soul wants to figure out or deduce what this term is going to look like in this equation? No wrong answer. Well, there are wrong answers, but
I have negative 1/2, and then for a I put f0 over m, and then for t I put v0 sine theta over g squared.
okay. Well, you just need t squared here.
Oh, okay.
You just need to, yeah. So, because what we're doing here is, so you're totally right that this is going to be negative, right? You're negative here, f naught over m. That's right. All we're trying to do here is we're trying to write x and y in terms of time, right? We're trying to write position functions for x and y respectively. So very good. That's exactly right, Alan. All right. Now, what about the y equation? Who has a guess about what y is going to be? Anyone? Peter? Oh, I didn't see the chat here. Critical. Oh, never mind. Differential equations. Oh. Yeah, I'm so sorry, guys. I'm not looking at the chat. I don't. I only have my computer and my monitor, and I'm looking at you guys on my main screen, and then the PowerPoint on my monitor. So it's like when stuff appears in the chat, I just don't see it. So yeah, I'm sorry. But anyway, so y direction? What do we think?
It's just v naught sine theta, because f is only in the x direction.
Right. So okay. So you're partly right. So you're right with this first term. It's going to be v naught sine theta. Very good. So you have that first part right. That is exactly right. But remember, the gravity is not gone in this setup here, right? We have a projectile motion problem, and in every projectile motion problem that you ever do, there's still gravity. All they've done here is, in addition to gravity, we now have a force in the x direction. We have a wind force, if you will. We'll call it a wind force. The force of the wind. We have Ang off in the distance. So, cool. So what's this next term going to be? Right, so there is clearly an acceleration term still in the y direction. What is it?
Minus 1/2 gt squared.
Yep, yeah, exactly, right. That's perfect, Andrew. Minus 1/2 gt squared. Excellent. And so the problem wants us to find where, for the given value, for a value of theta, where these two things end up back where they started, right? So, and where we started was the origin. So we really have a system of equations here, and I'm just going to get rid of x. And actually, before I get rid of these, so I just want to point out, so what we have here, right? So we have a useful set of equations here. These two equations are the x and y position functions of this, what is a ball. So these are the x and y position functions of the ball, right? These are both functions of time. The input is time, and the output is going to be x position, y position, respectively. Now, what we want to do is we want to find where we get back 0 in these cases, right? So, because we started at 0 and we want to end back at 0. So what we have now is we have a system of equations where we have two unknowns. And what are our two unknowns here? Okay, well, I'm going to grab a sip of water while we contemplate this question. What are our two unknowns? Well, for starters, we don't know the time, right? We have no idea how long this ball is going to be in the air. So time is one of our unknowns. But what's our other unknown here? What are we solving for?
Yeah.
Theta, right. So yeah, exactly. So our two unknowns, so we have a system of two equations with two unknowns, and our two unknowns are t and theta. So what we can do is we want to try and eliminate t to find an expression for theta, right? This is like back in 8th grade where we had y equals mx plus b and y equals mx plus b. You know, you had two linear equations and you're finding where they intersect. Now we have two equations and we want to find, algebraically their intersection point, but they're not linear equations anymore. But that's okay because we're about to make them linear. Because these are equal to 0, we can use the zero product property, right? So this equation is really going to become v cosine of theta minus 1/2 f naught over m t equals 0. Does that make sense what I did there? I just want to be very clear about what I did here. I did not divide by t necessarily, right? You got to be very careful when you divide by variables because there's solutions in nonlinear equations called extraneous solutions, And so in general, you don't want to divide by variables. What I did instead here was I factored out a t, and then I used the zero product property, right? Where if you have a, a plus b equals 0, you really have two equations, a equals 0 or a equals negative, or I should write it like this, a plus b equals 0. This is the zero product property. You can rewrite equations of this form like this. I'll assume that we already knew that, but I just want to make sure. So let's get rid of all that. So that's all I did here. I used zero product property. I did not divide by t. You got to be careful when you do things like that. And the same thing here. V naught sine theta minus 1/2 g t equals 0. Okay, great. Let's go ahead and solve for t in the y equation. Typically, when you do projectile motion problems, t in the y equation is going to determine the airborne time, right? Because your airborne time is determined by y. So the time spent in the air is going to be given to you by this y equation, because that's the one that deals with air time. That's the one that deals with vertical position. And so if we solve for t here, what do we get? We're going to end up with t, pray to God that I don't make an algebraic mistake here, but it's going to be 2 v naught sine of theta over g. Do we all agree? Okay.
Yes.
Okay, awesome. So this is the time that the ball spends in the air. And now if you go back, right, remember when I showed you those equations for projectile motion? The t at the top of the trajectory was v naught sine of theta over g. Notice that this is 2 times this, because when you have a symmetric parabola, or I mean, you don't have a symmetric parabola here exactly, but when you have a projectile that starts and stops at the same height, the time taken to reach the top is half the time taken to reach its maximum range. Again, I will assume that is a fact that you guys already knew, but if not, now you do. So anyway, so we have this value of t now. We can plug this in to our x equation to eliminate t and find what theta is. So we're going to have v naught cosine theta minus 1/2 f naught over m times 2 v naught sine of theta over g. And all of this, I'll say equals 0 right here. Everyone see what I did here? I just took t and I plugged it in right there. And then I rewrote it over here. You have a whole flow chart of math. So now all that's left to do is we just need to solve for theta. So we really have 1/2 f naught over m over 2 v naught sine theta over g equals v naught cosine theta. I just added this to this side. So what cancels here? Cancels. It's okay to cancel out these variables, by the way. I know I just made a point about not canceling out variables. You can cancel these ones out because we know they're not 0, right? V naught is not going to be 0. You only can't divide by variables that have the potential to be 0, as t was. But v naught is not that. 1/2 and 2 cancel. So, and then if we, so what do we end up with here? We end up with f naught over mg equals cosine over sine, which is cotangent to theta. And I totally did the problem on purpose this way, just to use cotangent. Because cotangent is not used pretty much ever. So might as well use it. Anyway, this becomes mg over f naught equals tangent to theta. And I think that you can see if you take the inverse tangent to both of these, you end up with answer choice B. And that's the answer.
Couldn't you have just like moved 1/2 f naught over mt to the right, and then 1/2 gt to the right, and then divided both of them so you don't have to solve for t.
Say it again.
Oh, so for the two equations, like after the first equation, or like even
Yeah.
using the first equation,
Two
couldn't,
equations.
Oh.
I'm sorry. Which one are you alluding to? These ones?
yeah, those two work too, but I meant the two after, but yeah, you could have just moved like 1/2 f naught over mt squared to the like left side in the first equation, or oh yeah, or to the right, and then 1/2 gt to the right, and then divided both equations, right? To cancel the
Oh
t's.
yeah, yeah. I mean, that'd be totally fine too. Oh, so okay. So you're saying add this to this side, add this to this side, right? And then take the quotient of those two equations.
Yeah.
Yeah, that'd be totally fine too. I mean, when you're solving linear systems of equations, right? There's either you could do substitution, you can do elimination. Yeah, I mean, so your method, I think, is technically, if I remember, that's elimination or something, or is elimination? I think is when you take the difference of the two equations. But yeah, I don't know. I did substitution here, and it got us the right answer. But that's fine. You could do that also. Yeah, good call. Any other questions? All right, then we will go ahead and clear all the drawings, and we will proceed. All right, here's a fun one. So a ball is launched upward from the ground at an initial vertical speed v0 and begins bouncing vertically. Every time it rebounds, it loses a proportion of the magnitude of its velocity due to the inelastic nature of the collision. I think tomorrow we'll do momentum and collisions. So again, this will be a nice segue into tomorrow. Or energy. Maybe we'll do energy tomorrow. I don't know. Anyway, so such that if the speed just before hitting the ground on a bounce is v, then the speed just after the bounce is rv, where r is some constant less than 1. Calculate the total length of the time the ball remains bouncing, assuming that any time associated with the actual contact the ball with the ground is negligible. Okay. Cool. So, does everyone follow what this one's asking? Give you a second more or two to think about it, and then we'll go ahead and jump right in. Okay. Well, let's say that we have a ball here, and I launch it up at speed v0. And it's going to come back down at speed v0. And then this tells us that it's going to bounce up at some other velocity, rv0, and then fall down at some other velocity, rv0. What's this next one going to be, by the way? What would this next term be? If I go here, what is the next velocity?
R2.
Right. I actually didn't even hear what was said, but I assume that was correct. R squared v0. Yep. Yeah. So every time you're just depending on another factor of r. So I think you guys might be able to see that this is turning into, well, it's going to turn into an infinite series at some point, and we will address that shortly. But so yes, so we have v0, v0, r v0, r v0, r squared v0, r squared v0. Okay, what is the time that the ball spends in the air here? And again, I will point you, and so this is why I showed you those equations at the very beginning of this meeting or this class period, because we're going to use those equations. Like I said, it's very handy to keep those, or it's a very good idea to keep those equations handy. So what was the time of flight equation, if anyone remembers? for a projectile. I mean, you can basically treat this as a projectile. This is essentially a vertically moving projectile because it's the only force acting on it while it's airborne is gravity. So it's a projectile in free fall, you could say. Anyone remember what the time of flight is?
V0 squared, V0 sine squared over G. 2V0 sine squared over G.
Yeah, okay, there you go. Yeah. So 2 V naught, but what is sine of theta here?
98 degrees, so 1.
Right. So you're exactly right, Ryan, that the time of flight here is 2 V naught over G. And that's for the ball to be launched here and then fall down, right? So boom. Time spent in the air here is 2 V naught over G. Okay. What about here? Well, it's going to be T equals 2 R V naught over G, where the new velocity term is R V naught, right? So here to here is this. Okay, and then same thing here. We're going to have, oh, that's not a pretty bright, that's not a pretty thing. This is going to be T equals 2R squared V naught over G. Does everyone get the idea? So if I call this T1, T2, and T3, the total time spent bouncing is going to be T1 plus T2 plus T3 dot 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 all the way to T infinity. T infinity. And you know, we can express this as an infinite sum by saying let's let n equal 1 to infinity, t equals n. Are we all on the same page with what I'm doing here so far?
Yes.
Okay, great. All right. So if we keep going, so what does that end up equaling then? Well, this is going to be 2 V naught over G plus 2 R V naught over G plus 2 R squared V naught over G dot 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 to be continued. From all these terms, we can factor out a 2 V naught over G. And what's left is 1 plus R squared, like that. So what we really have here, so the answer to this equation, so I'll say the total time, total t is going to equal, oh, hold on, that is probably the worst sigma I've ever drawn in my life. It's going to be 2 V naught over G of 1 plus, well, we can write it as this. We can say n equals 0 to infinity r to the n. Now this is where it actually ceases to be physics, right? Now this at this point is a math problem. So we've done all the physics. The physics stopped when we determined the time of flight, right? This was the physics. Now this is a math problem. So what is this? So this thing that we have here, what is this? Someone clue me in on what we have here.
A geometric series.
Yeah, there you go. Yes, we have a geometric series with a common ratio. Oh, I didn't mean to say that. I was going to ask what R is. So R is the common ratio, right? So we have a geometric series. And so I don't know how much you guys have studied series. Again, so series is typically a Calc 2 topic. And so geometric series are nice for the let me say this. What is the nice property of a geometric series? If people have learned this before. I'm not sure if you guys have ever learned this. So I could be asking a question that you guys genuinely would not know. So forgive me if that's the case. But Does anyone know like what makes a geometric series special? Okay, well, so a geometric series will always converge as long as our common ratio is less than or equal, or is the absolute value of our common ratio is less than 1. Right, so that's the unique property of a geometric series. Not all series converge, right? There's way more series that diverge than those that converge. And so geometric series, though, will always converge as long as the common ratio has a magnitude that's less than 1. And look at that, they told us that here. The common ratio, r, is less than 1. So we have a convergent series. So does anyone remember what the formula is for a convergent geometric series? Like, what is the sum equal?
I think it's 1/1 minus r.
That's right. Yep, it's 1/1 minus r. And actually, let me just be a little more specific. You're right, but that's the special case. The actual formula is a naught, the starting term, over 1 minus r. But in this case, what's a naught? What's the first term of our sequence? 1, right? This is a naught right here. So you know, in this particular case, it's 1. But in general, right, the sum of your series is going to be the first term over 1 minus r, the sum of your convergent geometric series. So cool. Well, that actually gives us the answer then. If we substitute a naught being 1, we actually end up with one of these answer choices. We get 2v naught over g is 1/1 minus r. And look at that. That was a pretty cool question, wasn't it? I was happy when I did that question. I felt like I did something. That one was a good one. Does anyone else feel the same way, or am I alone in feeling that way? Yeah, Ryan feels Ryan feels good about that one. Who else feels good about that one? Okay, Peter. All right, Andrew. All right, awesome. All right, well, maybe I overestimated how good this one was. All right. Anyway, so let's go ahead and clear all drawings. Are there any questions on that one? No. Okay. Let's go ahead and clear the drawings then. Let's go ahead and proceed to the next one. Oh, I have to stop annotating. What? Why isn't it? Ah, okay. There we go. Okay. Here's another interesting one. An observer stands on the side of the front of a stationary train. When the train starts moving with constant acceleration, it takes 5 seconds for the first car to pass the observer. How long will it take the 10th car to pass? So I'll give you guys a quick minute or so to digest this one, and then we'll go ahead and jump right into it. Okay. So, how are we feeling about this one? Mhm. All right, let's go ahead and think about it. So I've drawn here the train. Here's the first car of the train. I'll say that it's accelerating this way to the right. Here are all the train cars in between. We don't need to worry about those. Then here's the 10th car. And so we want to know, as it's moving past this observer, how long it takes, right? So this right here, this car took 5 seconds, right? That tells us that it took 5 seconds for the first car to pass the observer, which is what happened here. 5 seconds for this car to pass the observer. How long will it take this car to pass the observer? And so this is the mystery time. Okay, well, so this is a kinematics problem. What kinematics equation or what kinematic equation would be most useful to employ here?
The first one.
What's the first one? I'm so sorry, I don't.
X is equal to half a t squared.
Right, okay, that's exactly right. And so I'm just going to add in the other part to that also, 1/2 at squared. Yeah, also, I've never like enumerated these. So when you say the first one, you know, in my head, it's like the first one changes every day. So it's always a flurry. But anyway, but you're exactly right, Ryan, that this is the equation we want to use here. We want to use this equation because so we implicitly know the initial velocity, so we know this. Time is what we're concerned about. We certainly will want to make some reference to distance here, right? Because these train cars are passing by and distance is useful here. Final velocity we don't need, so it's not even in this equation. And you know, acceleration. So yeah, so this is the one that we want. Okay, so so can someone give me an expression for how long it took this first train car to pass? Give me an expression in terms of, and you know what? I'm going to define another variable here. I'm going to define this to be L for us. I'm introducing this variable. They don't give us this variable in the problem. I'm introducing this variable. It'll go away by the time we get the final answer. But for now, we'll just introduce it. It'll be helpful. So, yeah, so anyone, an expression for how long it takes the first car to pass.
L is equal to 1/2 a times 5 squared, or 25.
Mm-hmm. Yes, that's right. Exactly right. Does that make sense, everyone? All we did here is we took this kinematic equation that Ryan pointed out earlier, and we substituted in the values we know. The only one we know is really that this is 0. We know that the initial velocity is 0. The train starts at rest.
The train starts at moving.
I'm sorry?
I'm pretty sure the train starts at moving.
It starts stationary and then it starts moving.
Yeah. So it stands on the side of stationary train. Yeah.
Whoops, I read it wrong.
Yeah. No worries. But yeah. So if it were moving, that would change things a little bit. But thankfully, it's not moving at the start. Yeah. So initial velocity is 0, and so that leaves us with L, right? This displacement here, I should call this delta x. The displacement from start to finish of the train car is L. So L equals 1/2 a t squared, and we were given that it takes 5 seconds. So you are exactly right, Ryan, that this is the equation. Okay, and now hypothetically, I want the equations now at these other 2 points. I want the equation at this point, and I want the equation at this point. And any brave souls willing to do that? Ryan, take a break for a moment. I want to give some other people the chance to figure out what this might be. So
the one on the right the one on the right would be 9L equals 1/2 a t squared plus v naught t, or yeah, so then you can solve for v naught by solving for the velocity after it passes the first car, right?
Okay, so you're definitely on the right track. I would not reintroduce velocity here, though. There's a way to do this problem without velocity, and that is the way I advise doing it. But you're totally on the right track. We're gonna call this t, but it's gonna be some unknown time. We don't know what this time is, so I'm gonna call it t prime. We're gonna call it t prime. But other than that, you're exactly right, Alan. That it's gonna be 9L equals 1/2 a t prime. So
Squared, right? Is it squared?
I'm so sorry. You're right. There should be a square here also. Thank you. Thank you. Yes, and so someone else tell me why there's a 9 here. Where did the 9 come from?
The displacement between the first car and the 10th car.
I'm sorry, who was just talking? I can't even.
Peter.
Oh, Peter. Okay, great. Yes. Okay. So, say that again. I'm so sorry. It was
The displacement between the 10th car and the first car.
right. Yeah. So it is the distance between the start of the 10th car and the start of the first car. Right. There's 9 L's between this point where it starts and this point. So very good. All right. Now the equation for this side. What's the equation on this side going to be? Very similar to this one.
That's 10L equals 1/2 AT squared.
Yep. 10L equals 1/2 A. Now t in this case, we got to be careful. It's not going to be the same t, right? This t is different from this t. Some time has elapsed between these 2 points. So it'll be, let's call it t double prime. Now, okay. What we want to do here, delta t, right? The time taken for the 10th car to elapse is going to be t double prime minus t prime. Do we all agree with that? It's going to be the time at which the train passed the observer here, at which this part of the train passed the observer, minus the time at which this part of the train passed the observer. That difference gives you the total time it took for the 10th car to pass by the observer, right? So, and actually maybe what I should do here is, so this is going to be 10L. Actually, let me do like this. This is going to be, so t double prime is going to be 10. Let me draw that a little neater. It's going to be 10 2L over A, and all this is going to be under a radical. Do we all agree? Okay, by the same token, this is going to be 9 times 2L over A. Do we all agree? Very good. So you may be wondering right now, well, what's 2L over A? Well, very good question. We can find 2L over A using this right here. If we solve, or if we write everything here, 2L over A, it equals 25. So we have 2L over A and 2L over A, and we have a numerical value for that quotient. It's 25, right? It's the square of the initial time that it took for the first car to pass. So what we end up with is 10 times 25 minus 9 times 25. We can factor out the 25s, right? We can factor out the root 25s and end up with 5 square root 10 minus square root 9. Does everyone make sense what I did up to this point? Okay. Well, I don't actually know how they would have expected you to get this, in your head. I mean, the square root of 9 is 3. We all know that. The square root of 10 is around 3.16, but I don't know why. I mean, and so I just want to make it clear, I did not know that off the top of my head. When I computed this, when I was doing this problem, in fact, when I did this problem, I left it in this form. And I'm not sure what they are going to do, expected, because, without a calculator, I don't see how you would know what the square root of root 10 is. And some of these answer choices, I mean, like these answer choices here are actually kind of close. So, I mean, it's going to be really sensitive to your approximation of root 10. So, but it is 3.16.
I think we get a basic calculator on the test at least.
Okay, got it. I mean, I took F equals MA over 6 years ago, so I don't even remember if the policies are different now. But so it is about 3.16, and so 3.16 minus 3, so it's going to be 5 times 0.16, which is 0.8. And we only approximated the square root of 10, and the closest answer choice is this one, E, and that is the correct answer. Cool. So how do we feel about that one? I mean, I'm curious what the general impression of this question was. I mean, so when you guys saw this question, and what was the general level of difficulty that you thought this question was? I mean, did you, if 10, you read this question and thought, oh my gosh, this is a hard question, or 0 being, oh, I already had this solved before we even started doing this. I'm curious. Let me know what you guys thought about the difficulty of this one. I'm genuinely curious. I'll just let you know, I personally thought this one was a challenging one.
I thought it was like kind of medium hard. I read it as like how long it will take for the whole train to pass. So then I got like a bigger number, but then I was able to find the correct answer.
Right. Okay, got it. Anyone else? Any ideas on what we thought of this one when we were going into it?
Like a 5 out of 10.
5 out of 10. Who said that? Oh, Ryan. Okay, got it. Okay. Cool. All right. Well, let's go ahead and clear all drawings then, and let's go ahead to the very last one we have. So this one. So consider a dripping faucet, where the faucet is 10 centimeters above the sink. The time between drops is such that when one drop hits the sink, one is in the air and another is about to drop. At what height above the sink will the drop in the air be right as the drop hits the sink? At what height above the sink will the drop in the air be right as the drop hits the sink? That last sentence is a little confusing, but I think that if you read it 2 or 3 times, it starts to make sense. So I'll give you a minute to think about this one, and then we'll jump into it. Yeah, so at what height above the sink will the drop in the air be right as the drop hits the sink? That's the question. Yeah, so let's imagine that we have a little faucet here. All right. So I'll actually give maybe one more minute, and I actually, I actually want you guys to send me, you can do it publicly if you want, send me a private message if you don't want to share publicly of what you think the answer choice is. When you feel confident in an answer. And I just want to clarify something, that the question is asking at what height above the sink will this drop be when this one hits the sink? Right, so it'll still be a distance from here to here, wherever this drop is, here to here. All right, anyone else want to share possible answers with me? We only have a couple. If you're not sure, that's totally fine, but if you do have, put in a guess, right? Because on F equals MA, right, you're at least going to attempt every question. So give me a guess if you're not sure. Okay. Yeah, and if you're still solving, no problem. No problem. Okay, we have about 6 minutes left. Yeah, so we'll go ahead and jump right into this one. Okay. So, all right, so I'm curious, did you guys do calculations for this one? Because I think the best way to do this problem actually is to do it qualitatively. I think that there's a very easily conceptual way to see this problem. So when I did this problem, I did no calculations at all. Conceptually, there should be a way to think through this one. So anyway, so here would be my thought process if I were approaching this problem from a conceptual point of view. You know that this drop here, this drop is starting from rest, right? V naught is equal to 0. This drop, when this one falls out, starting at rest, has some velocity, let's say V1, right? You know then that whatever, for all time t that they're falling, the velocity difference between these two, is always going to be V1, right? Delta V between these two drops is always going to be the velocity that this one was when this one fell. And I'm calling that V1. Does that make sense? So there's always going to be a velocity difference. And take note of this, because on the problem set that I made for you guys later, there's another problem that makes use of exactly this concept of two things falling at different times. The thing that remains constant between them is the velocity difference between them, because they have the same accelerations, right? They have the same accelerations, so their velocities will increase at the same rate, but their differences in velocities will be the same, which is going to be V1. So whatever distance this happens to be, right? I mean, let's say that this distance was like 5 centimeters. It doesn't have to be 5 centimeters, but 5 centimeters is, roughly probably when this other drop would fall. If it's going to be falling for another, so if the position between these two maintained for the same amount of time, and these fell, maintaining the same separation between them, then the answer would be 5. This would hit the ground when this one's 5 above the surface. But they're not going to maintain the same separation between them, right? The separation between these two drops is going to increase because of the fact that there's a velocity difference between them. There's a relative velocity difference between them. They have the same acceleration, but because this one starts at a different velocity and they have the same acceleration, this one's always going to be gaining a little bit of ground on this first drop, right? For every little piece of time that passes, this one gets a little bit farther ahead of this one, right? So whatever distance this is, let's say d, the final distance is going to be d plus some amount, d plus v times t, where t is the time taken for this to hit the ground, this drop to hit the ground. And so if this one starts falling around halfway through, right, the only place that this one can be, given that the separation between them is increasing, when this one hits the ground, is going to be between 6 to 8 centimeters, which is d. And like I said, I did not do any calculations for this one. But that's how you would approach this from a conceptual point of view. You know that the velocity difference between these two has to be the same, so that when the two drops are airborne together, the one that has already fallen is going to gain ground on the drop that just fell in that little time interval for which they're both airborne. And it's the fact that there's that gaining of distance that makes it around 6 to 8, assuming this falls around the halfway mark. Does that make sense? If you did attach some numbers to this, you should end up with, like if you did solve this with numbers, which we could also do, because I did this with numbers also earlier. I don't know where I put that though. You could find that if you assume that this starts at like 5 centimeters, like this one falls, well, this one's at 5 centimeters, then you can find that the separation between them when this one falls is roughly 7 centimeters. And if the separation between them is 7 centimeters, then this is the only interval that contains 7. Does that kind of make sense? Thumbs up if that makes sense.
How would you assume that it's like 5 centimeters?
Well, okay, yeah, well, that's a good question. I mean, so when I did this problem, I assumed it was 5 centimeters, but even if you didn't assume it was 5 centimeters, right? Even if you assumed that it was something smaller than 5 centimeters, right? The point is that the distance between them is going to increase. And if it starts farther up here, it's going to be airborne for a greater amount of time, right? So the distance between them is going to increase. And yeah, and I think that I mean, they don't say this in the question, but I would assume that they mean that this drop falls roughly around the midpoint when this one starts. Like this drop falls out of the faucet when this one is nearer to the midpoint than not. Right? Because if it falls right, way down here or way up here, then that would change the answer. But the answer to this one is 6 to 8 centimeters, which necessitates that this one's falling kind of close to the midpoint. So I think that's an implicit assumption that they built into the question, but didn't state outright.
Could you, between like the drop on the floor and the drop in the air and the drop in the faucet, wouldn't it be the same time interval between all of them? And then that's how I solved it. I just like solved for the total time that it dropped, and then I just split it in half to solve for the time in between the top and then the one in the air.
Right. Okay. Yeah. So, okay. So what time did you? So you took the time that it took to go from here to here.
Yeah.
You found that total time,
Yeah.
right?
And then divided it
Then
by
you
2.
divided it by 2
Yeah.
to mark when the next drop would fall.
Yeah. And then
Right. Oh, yeah. And that's totally legitimate. In fact, if you attach numbers to it, because I think if you attach numbers to it, that's what gives you, between 6 and 8 centimeters, because then you get a final separation of, I think it was like 7.14 when I worked out the numbers.
Yeah, I got 7.25.
Okay. Yeah. Then there you go. So that's why it's 6 to 8. But like I said, when I was deciding how I should explain this one, I didn't know if I should do it with numbers or do it conceptually. I thought the conceptual explanation was a little more easy to see. So, but that's right. If you wanted to do it with numbers and more rigorously justify why I put this at the midpoint, you would do it like that, or kind of close to the midpoint. So, cool. All right. Well, are there any questions then? That was actually the last one, so I guess that was good timing. Before you guys go though, well, so actually first, are there any questions? No questions? No questions about anything today? I think tomorrow we'll do, I don't know if we should do energy tomorrow or momentum and collisions. We'll do one of the two tomorrow. Because there's a lot of cool problems with energy, but there's also a lot of cool problems with momentum.
Why not do both?
Why? I don't want to do both at once. Oh, I mean, we could do both at once. I don't know. I mean, who suggested that? We could do both at once. But they seem like different enough topics. I don't know. Okay, anyway, so before you, because I know it's noon and I want to be respectful of your guys' time. So before you go, I would appreciate actually if you guys could send me another private chat on your impression of the difficulty of these problems, right? I mean, because like I said, I want to try and make this as beneficial for you guys as possible. So, I mean, are these problems too easy? The ones that we're doing in lecture, are they too difficult? Please let me know. I mean, so the quiz questions, those are supposed to be diagnostic. But as far as the problem set questions go, or these questions, please let me know. Are they too difficult, too easy? Do you want more difficult questions? Do you want easier questions? Because a lot of the questions we're doing are actual past F equals MA exam questions. And not all of them. I'd say like 50% of them are. So, okay. Yeah. And then once you've told me what you think of these questions and any suggestions you have for improvements, you are free to go. I'll see you tomorrow. Thanks for coming by. Enjoy the rest of your day.